Right. So today we'll just focus on the PowerPoint slides that we have. It does take a little while to discuss. We'll just do that. And as you can see, the things that I've written on the board, that's what we'll be doing in the next couple of lessons this week. So there is an assignment to do. The assignment is just the code stuff. So you've done that before, you know, Angry Birds, all that kind of stuff. So let's continue with that. Exercise 10, 12, 15, and 16. There is a lab, which is a flowchart type lab, and a tracing, which I will show you how to do in the tutorial. Tutorial is tracing and flowchart. Now they are integrated into this topic because in the flowcharts that we'll do and in the tracing, I'll teach you how to do tracing, but in the tracing that we'll do, it will be with programs that have loops in them. So that's our topic. Now, as you see, the topic is not one thing. It's not just loops, it's loops and variables. So the first few minutes will be about loops, and then we'll talk about variables because the idea of variables works with another idea called states. And we have to understand states to do the tracing, which we're going to talk about in the tutorial. So there's a bit to think about in this lesson. So loops comes from the idea of being able to repeat different commands in our program, in our algorithm. Repeating is important. It harnesses or takes advantage of the extreme power of the computer, which is to do things very quickly, because a computer has a clock in it. You would remember that, right? And you know the clock speeds are so fast. We're talking billions of cycles per second. So for example, you have a gigahertz processor, 2.4 gigahertz. So 2.4 gigahertz means that you've got 2.4 billion cycles per second. Billion is a lot. That's 1,000 million, right? And now you know that we've got the Van Neumann architecture. So a cycle doesn't mean a executed instruction. You'd have to multiply that by about 3 to get how many cycles per instruction. But even still, so that means dividing 2.4 by 3, you got about 800 million instructions per second. Now that is the power of our computer. It's not smarter than us, right? It's not that they think any better, but they can just do things very fast. And so how we harness that is by getting a simple instruction and repeating it. And repeating it very, very quickly. That is the power of our computer. So what would we repeat? For example, if you had a computer program that you needed to calculate everybody's tax that they're supposed to pay, right? You could have a database and all of the transactions that they had with the government, maybe all the stuff they bought, or in some places they pay tax on their income. You could have a database that had all that, and very quickly you could repeat the same calculation over and over again for millions of people. That would take a long time for people to do by hand with calculators, but on a computer, millions of them could be done fairly quickly. Yes, so hopefully you're familiar with the idea of the flowchart here. These symbols you will notice. So we've got our input symbol, which is this parallelogram without the square corners. We've got our start and end symbols, which are these sort of rounded edged things. This is supposed to represent a repetition loop. We also use the word iteration. There is something wrong with this because it's missing one of the symbols that is very important to a loop. And that is, of course, the diamond symbol. The diamond symbol is where we have a condition, which is either true or false. And that is how we control all our loops. You've already learned about if then else with diamonds. We use something like that in our loops. But we'd use something that would be called a while statement or a for statement, but it would work in that way. Now, as this slide says, there are 2 main ways that we can use loops, or there are 2 main ways that we can control loops, which are mentioned at the very bottom of this slide. And they are the counted loop and the Sentinel loop. So with a counted loop, what we do is before we try and repeat a bunch of code, we initialize a counter. Initialize means to set to its initial value. Initial means the first. So we set to its initial value, a value. Usually we start with a 0 or a 1, and then we add to it every time we go through the loop. And when we get to a certain value, we say we've done it enough times. So a value that we have decided on before we get into the loop. So for example, we want to repeat this 1,000 times. So we'd set a counter to 1 or 0. Let's say we set it to 1. And then every time we go through the loop, we add 1 to the counter. When the counter becomes 1,000, then we stop. So that's a counted loop. But the thing about a counted loop is we use that when we know how many times we're going to do it. Before we do it, we know how many times. Now, sometimes we're going to repeat things and we don't know how many times we're going to do it. So we might have a program which is asking people to register their children. And so every father, let's say, has to register all their children. So it'd be a question like, do you have children? Yes. Okay. What is the name of your first child? You know, and what is the name of your second child? When are we going to stop? Right? You know, some people will stop after 1 child. Some people will stop after 2. Some people will stop after 5, right? So when will we stop? We'll stop when the person says, well, that's my last child. And so that is a different kind of loop. We don't know how many when we start. And so we would have some other way of controlling it. The other way we control it would be this thing called Sentinel. We might ask the person, do you have another child? Yes. Okay, so give me the details. Or they'd say, no, I don't have any more children. You've got all the details of my children. And so now we stop. Does that make sense? So that's a typical way of doing that with the Sentinel loop. And I hope that makes sense to you, right? It's pretty obvious. Like some people have 2 kids, some people have 1 kid, some people have more, some people have none, right? And so we would use a different way of, we would control them not with a counted number. So the counted loop, as I said, before we enter the loop, before we try, everything okay back there, ladies? Good? Before we enter the loop, what we have to do is we know how many times we're going to do it. That's the only way that we would do a counted loop. So, for example, when we had the punishment thing, usually, I don't know, this never ever happened to me. Oh, that's not true. I believe it did happen to me. Maybe when I was like 8 years old or something like that. But, you know, right on the board, you know, a lot of times that you will not do some bad thing. Yeah, all right. So this is the punishment thing. Before you start, you know how many times you're going to do it, right? Write out 100 times. I will not be late to class, or I will not, whatever it was. I will not throw things in class or whatever what you do when you're 8 years old. So we knew how many times we were going to do it before we started the loop. So we'd do a counter. Okay, so count is equal to 0. Every time I print that I'm going to not do that bad thing, I add 1 to the count. When I get to 10, I get to stop. And so it could be something like this. Now this flow chart is not correct. It's not complete. It's missing a couple of elements, but maybe if you study it, you can see what it's missing. But it's better than the one that we saw a minute ago because at least it has the diamond. So we've got a diamond that we can use to control that flow chart. When the number of iterations reaches 10, then we're going to stop. But the problem is we haven't set the number of iterations anywhere. So before we actually enter that possibility of loop, we need to set the count, and then we need to add to it in there. So we're going to do that there, right? So this is what I mean. So here's our initialization where we are setting the count to 0. I've used the word count. Here it calls it number of iterations. Number of iterations, we could say number of loops, whatever, number of repeats. We use this term increment. Increment means to add a small amount to. So the place where people usually hear this word is on that happy day after they've worked at a job for a year or something like that. Maybe every year you get a pay rise. They will call it an increment, right? So, you know, last year I was getting so many thousand of reals per month. On the anniversary of my my joining, maybe I'll get an extra 2,000 reals per month or something like that. That would be an increment. And so people look forward to that. So we would do that with our count. Every time we go through the loop, we increment it by 1. Add 1 to it, add 1. So here we could apply that, I suppose. And let me see if I can do this in a flow chart. I'll try and draw a flow chart behind, behind me because I'm recording this. So if we start, this is going to be the homework one, is it? All right. So happy birthday. Oh no, happy birthday. The person is going to enter their age, and then we're going to display happy birthday however many times their age is. So what we would do is we would get their age. This is a type of input. Get age. Age is a variable. So you could say that's input. You know that input and output, we use a symbol like this, right? So we're going to get their age. Then what we're going to do is however many times their age is, before we do that, let's initialize the count. Count is equal to 0. Yeah, okay, count is equal to 0. So notice that this is got the square edges. It's got the square edges because it's a process, whereas this is an input process. Then what we're going to do is we're going to say, is the count, so no, what we'll do is we'll print happy birthday, output, and output happy birthday. And then we could add to the count, increment the count, count takes the value. Now notice I'm using the symbol that looks like a mathematical equal, but it doesn't mean a mathematical equal, because look at what I'm going to put after it. I'm going to say count takes the value of count. That makes sense. Count equals count. But I'm saying count plus 1. Well, that can't be true. You never saw a mathematical equation like that, right? It doesn't mean that this is equal to that. What it means is whatever was in the count variable, we add 1 to it and we store it back in the count variable. So here we're creating the count variable and we're storing the value 0 to it. Here we're adding 1 to that. So after this, the first time, count will now be 1. Yes. You're correct. The output should be like that. Thank you. And so here's another process. Now, after we've done that, we need to know if we're going to do it again. So I'm sorry about this. Yeah. No, I can't really move it. I can make it go down a bit. Maybe you can see it. Can you see that better? Is that better? But what I would put there would be, all right, so is the count less than the age? And if the count is less than the age, if that's a yes, then we go back here and we print happy birthday again. But if it's not, then we're done. So what's going to happen is well, if the count starts out as 0, right? We print happy birthday. We add 1 to the count. Then we check, is the count less than the age? Now, we got the age here. Let's say they said their age is 6. So is count less than 6? Yes, because count is 1, right? And so what will happen is we'll then go there and we'll print happy birthday again. And then we'll add 1 to the count. Now count will be 2. We'll print, we printed happy birthday twice. Is 2 less than 6? Yes. So we go back there again, print happy birthday again, the third time. We add 1 to the count. Count's now 3, right? Is it less than age? Yes, because age is still 6. Age hasn't changed, right? We keep doing that until count becomes 6, then we stop. Do you believe me?
We also need the birthday.
We don't need their birthday because they are telling us their age. So let me show you what I mean by this. You may have seen me use this before. IDLE is the IDE, which is Integrated Development Environment for Python. You can download this for free on your computers. Just go to python.org and you'll be able to download the latest version of Python. It's free. All right. It's not like you're stealing it or anything. They give it to you for free. And so you can do this at home or wherever you like. So I'm going to make a program here. I'm going to call it Happy Birthday. And what we're going to do is this. So the first thing there is get the age. So I'm going to create a variable called age. Can you read that? Is that big enough so you can read it? Can you read that that says age? Age takes the value. So I'm using equal, but that doesn't mean equal like in math equal. It means takes the value. age takes the value of an integer. So that's why I put an integer that is given to me by the user. The input, the idea of the input there is that the user is going to have a prompt given to them. So that's why it says there prompt. And so I will give a prompt, which will be age, which is just to remind the user what they're supposed to do when they get here. So they'll see, the user will see age will come on the screen, and then they'll type something, and whatever they will type will be converted to an integer and stored in the variable called age. So there's a lot going on in that little statement, right? The screen, they're going to have something come on the screen, which is going to be a prompt, which says, what is the age? Then that is going to be converted to an integer when they type, the user will type something in, that'll be converted to an integer and stored in the variable called age. That's the first thing. Then the next thing that happens is we do a count, takes a value of 0. This, what happens in this line of code is a variable called count is assigned a place in the memory, and the value of 0 is put into it. All right, so we have a variable called age, and we got a variable called count that are happening at that point. Now we can, well, let's just see. We can prove that by doing a print statement. What I can do here is let's do a print, and in the print statement, we'll print the age. And we'll print the count so that you can see what's happening to these as this so this is another way of doing a trace, I guess you could say. And so we've done that. Now we're going to print happy birthday, because we said that we would do that. Output happy birthday. We're outputting a bit more because I wanted to see what's going on in the program, right? Output happy birthday. And then we're going to have some way of controlling the loop. I'm going to use a while the count is less than age. Actually, I could have done this. It doesn't matter which way. Yeah, actually, yeah, while the count is less than the age, what I'm actually going to do is I'm going to take that and I'm going to put it here. So now notice that I'm indenting. That means that this is going to be part of the loop. The while statement creates a loop. So what's going to happen is it's going to print happy birthday, and then it's going to add 1 to the count. So this is incrementing the count. And what I'm going to do there is I'm going to print this all again so that we can see what happens as we go. So now each of these could have a line of code. So I'm just going to put the line numbers here. So this is line number 1. This is line number 2. Line number 3. Line number 4. Line number 5. Sorry, this is boring. Now, when I in Python, when I put a hash, what that means is this is not going to be part of the program. It's just a comment. Anything that follows the hash on the line is just a comment. So what I want to do here is I want to say what line we're on. So this is line 3. So I'm going to put that there. So age, I'm going to put a hash in 3 so that we know that this is line 3. And what other, okay, so this is line 5. So I'm going to put a hash and a 5. And this is line 7, right? So a hash and 7. So we can tell, we can see how the cycling works in the program. So that's okay. Count. All right, that's it, right? And then there's the end. So I could do a print at the end. Why not? And the end is what? That would be, this is going to be line number 8, right? And that's the end. And if I wanted, I could, just to make sure I knew what was going on, I could copy, I could do another print of everything that's happening there. Oh, sorry, that was lucky. That's 7. I hit the Control V instead of the Control C. See, let's go there. And this is line 9. All right, let's run it and see. Yeah, it should be less than or equal to. So let's see. Did I have less than? I forgot to put who? Yeah, very good. And that tells me that I did. Well, count is less than age. Age, blah, blah, count that. Let's run it again. So let's say, let's do a small age so we can follow it very easily. Well, let's just do an age of 3. So when the age is 3, so we see this is line 3, the age is 3 and the count is 0. Let's see if we can follow that in our program. At line 3, oh, sorry. Here's line 3, right? At this point, it says that the age is 3, and that's because the user when the user was prompted with age, they typed 3. So that now the age is 3, but the count is 0 because we set the count to 0. So the next line is going to be line 4. Nothing will be printed that, but the next thing to be printed would be line 5, and that's happy birthday. And there we go, line 5. Then the next line then count is going to be incremented in line 6, and that will, and line 7 will print what's the new count. If we look there, we see, okay, the age doesn't change, but the count does. You see the count change? Went to 1. Then what happens then is, you see, we went from line, I should have printed, what is that line number? How did that get missed? Let me run that again. So line number 7. Let me run this again. Let's close that. Let's do it with just a very small one. Let's just do it with 2. So it's easy to follow. The age is 2. It should be very easy to follow. So what we see, all right, on line 3, sorry, we asked them their age, they said 2. The first thing we printed was their age, 2, and the count 0. Then we printed happy birthday from line 5. Then the next line that we print is line 7, and that's their age, but see how the count went up. Then the next thing after line 7 is we go back to line 5. Why are we going back to line 5 after line 7? Because we're in the loop. The loop is going to repeat everything that's inside here until the count gets to the count that we've said that we'll stop at. Does that make sense? That's the repeat. That's that we have in our program. What I'm trying to do here is I'm trying to make this window smaller. So we see, we keep on repeating 5 and 7, 5 and 7, line 5, line 7, right? Well, obviously we repeat line 6 as well. So we see that the count went from 0 to 1 to 2. When it got to 2, we quit the while loop and we go out to the end. And so that's why we have line 8 is the end. This actually should say line 9. Sorry. Does that make sense? Do I need to run it one more time? You okay? Just one more time. I don't want it to get too boring for you. Just make sure we've got it. Let's run it. Let's do it with a bigger number so that you know that it actually works. Let's say somebody more like you, age 19, we see that changing, right? So we see the count going through 1, 2, 3, 4. The age never changes, but the count goes all the way up until it becomes 19, and that's when the program ends. Doesn't end until we get to 19. I know it's hard to see down the bottom there, but down the bottom, it does actually say 19. That's when it ends. Okay. So that was kind of fun for me. I don't know, maybe it's not fun for you, but hopefully. So we've done that. So that loop that we just did, that was a counted loop. We counted. When we got to the number, which was the target, that's when we stopped. The next kind of loop is a Sentinel loop. With the Sentinel loop, we don't know when we're going to stop, but we get the user to enter something which will be like a Sentinel value, some like magic word, right? And at that point, we will stop. And so there's, as it says, we would only do this when we don't know how many times we're going to do it. So an example that we've got here is we've got a restaurant or some other kind of shop that sells things. And during a day, we're going to sell a lot of things. And then at the end, we're going to get the total for the day. Well, some days is going to be different than others, right? We don't know at the start of the day how many times we're going to sell something. And so how are we going to know when to stop adding the sales? And so, well, you could come up with some kind of bodgy sort of answer like this. I don't really like it, but you know, what could we do, right? So we could enter in a value of 0. So we'll say, all right, salespeople, this is what we're going to do. We're going to keep adding sales to the total. When you're finished, type 0, and that'll be the end. Okay, that'll work. Now, why would 0 work? Because it won't add anything to the total. It won't mess up the total. That's one reason. And the other reason is that you're never going to have a sale of 0, right? So we'll know that there's something strange about that. And what's strange about that is our indication that we're finished this program, or we finished the loop. And so look at the flow chart here. We got input, asking them for the amount that's sale. We add that to the total. We're actually missing a couple of things. We probably should have a total sales initialization to 0 first. And then we get the total sales. And when the sale becomes 0, we stop. All right. And so you have to be careful with this. That's what that slide is saying. You don't want to put it like a negative number in there as a sales. That would be a good Sentinel value, actually, a negative number, because nobody's going to ever have a negative sale. But if you put a negative number in there, you wouldn't want that negative number added to the total, because that would mess up your totals. So be careful with your using of your values. Now, here's one that we could use. I will not cheat on my assessments. But the user gets to say, instead of saying we're going to do it 100 times, we're going to do it until the person says, I don't want to do it anymore. Basically, what it says here is we're going to say, print it again. What I'll do is I'll say, print it again, yes or no. So we would do just simple. This is a fairly simple one. We would start. There's no input from the user to start with. There's just an output of print. I will not, whatever the bad thing it was that we will not do, I will not. We're going to print that. And then we're going to get a response from the user. So this is going to be an input. Repeat. Sorry, do it again. Or stop. I'm just going to say do again. Input, do again. So we're going to ask them if they want to do it again. Yes or no. So that's going to be an input. The user is going to be given a chance to say yes or no. Now, depending on what they put, maybe they put yes, or maybe they put no, right? So if they put yes, do it again. We do it again. If they say no, don't do it again. And we finish. Pretty straightforward, right? We could do that as a program just to, I hope this doesn't bore you too much, but let me do that as an idle program just to prove to you that it works. So we've got a program there. Let's make a new one. And this will be the I will not program, right? I will not. So what we're going to do is we're going to say I will not do something. And then we're going to ask them to if they're going to continue. So that would be, let me give a variable and we'll call it again. Again is going to be, we're just going to ask them to input a yes or a no. Y or no. And then all we have to do, oh, well, that's why that didn't go down, because I didn't close the quote. Then all we have to do is test it, right? So we could do that with a while. Oh, we could do all of this in a while statement. No, we can do a while here. While again is equal to. Now this kind of equal to, this is like a mathematical equal to. This is different than the one equals. Two equals means, are the two things on either side the same? So that's like your math equal. So we had to make it look different in Python so that it would work. So is it equal to y? Or we could say, is it equal to big Y? Because maybe the person's going to put a big Y in, right? So while it's equal to either of those things, what we'll do is we keep doing this. I'm not going to put the, let's run it and see. I will not. So I got an invalid syntax there. Or again, good if I put the equal symbol in there. All right, so sorry, we got the old program running on there. Let's run it without. The old program wasn't running, but the output from the old program was still there. So I'd get a clean output without old program. So I will not repeat again. So as long as I type Y, it will repeat again. But as soon as I type something else, which is not a Y, it won't repeat again. Does that make sense? So that's how that one worked. This is a Sentinel loop. As soon as I type something different, I don't have to type N, but anything that's not a Y, that stops. Make sense? Sentinel loop, different than the counted loop. I didn't know how many times I was going to do it until I did it. And I had some way of controlling it, you know, it's by the thing. This is the Sentinel. All right, so, right. When do we use a counted loop? When do we use a Sentinel loop? We use a counted loop when, before we start the loop, we know how many times we're going to do it. When do we use a Sentinel loop? We don't know how many times we're going to do it until we get into it, right? The user is going to tell us how many times. How many children have you got, right? You know, keep adding until you run out of children. Or how many times do you want to write? I will not. Well, at some point, you're going to get tired. Some people get tired at 100. Some people get tired at 1. All right. Stop. New topic. All right. So today we have 2 topics. We just went over the topic of repetition. So the next topic is about memory and states and variables. So we have to use variables to do this kind of program. The variables that we used were count, right? Used age, and we used again those variables, and we put values into those variables. And those variables changed depending on what happened in the program. So when we looked at our program, for example, when we were running the happy birthday one, did you see how the count changed? Every time we went through the loop, the count changed. When we did the I will not, the again changed depending on what the user did. So that is how we measure what's happening with the program. That's how we control the program. We use our variables to do that. And so how a variable works is, do you remember the computer architecture classes that we talked about in the first couple of lessons? We said that the computer memory has addressable memories. Computer memory only holds zeros and ones. All right, so that's a bit of a trick. So everything that we do to communicate with the computer, that has to be translated into computer zeros and ones, and then retranslated back when we want to read it, right? So that is possible with the computer through the operating system. But the computer memory itself is only storing zeros and ones. Luckily, each different memory location has an address and can be accessed by the index. So that index to that address is then assigned to a variable, and we give them a name. And so once that variable is attached to an index address in the memory, we can put things into that memory position and we can retrieve them later. And we can change them. We can update them. And that's what we were doing in the program when we said count takes the value of 0. What that means is we created a memory. In the memory, we created a variable which had an address, and we put a value in it. And then later we change that value and we read that value out. We can do all of those things. That's all that we need to sort of say about that. I think there is a related thing to a variable, which is called a constant. Variable means it can change. Constants don't change. Don't change when? Change when? During the life of the program. So, I mean, you turn on your computer, you start a program running. At that time, the memory of the computer is going to have the program code loaded up, and the variable will be created as the program goes. All right, once the program is finished, the variable disappears, right? Everything disappears. Yeah, so the constant would be not changed during the life of the program. So we start the program until the program ends, the constant has the same value. With a variable, it may change, right? We can create new variables and we can change the values during the time of the program. That's all. So why would we use a constant? We might have values that we just don't want to change. So for example, if we had a value that represented a mathematical constant, like for example, pi, which is calculated based on the geometry of a circle, the value of pi never changes. And so if we're going to use pi in any calculation, we would use it as a constant. It wouldn't be something that would change during the life of our program. Other ones like the speed of light. Yeah. Okay, speed of light is used as a constant in many physical equations. Does actually change a little bit depending on the medium that the light is traveling through, but it doesn't change very much. For our purposes, we'll just say that the speed of light is a constant. And there's lots of other constants. Gravity, G for gravity, you know, and acceleration, a lot of physical constants. Pi is good enough as an example. Now, the slide that I'm showing you now represents the fact that we have some rules. If you don't follow the rule, doesn't mean your program won't work. What it means is that your program won't be very readable. And if you don't have a readable program, then it'll be more work for you to edit it and fix it and read it. And it'll definitely be a lot more work for anybody else who didn't write the program to come along later and try and understand what's going on and maybe fix the program. So we have some rules that we apply to ourselves that make it easier to read, fix, update programs. And so, for example, for variables, one of the rules that we use is we use a lower camel case sort of way of doing it. And so what that means is a variable will all be lowercase, except for second and third words that are added to the variable name. So in this case, we've got a variable which is made up of two names, and we don't put any space between them, but the second name we capitalize. That's called lower camel case. Now, as I said, these rules, if you broke the rule, it wouldn't mean that your program wouldn't work, just mean that it would be very hard to fix it. I mean, you could have a variable that was just called S, and that would be student name. It will work, but you know, you come back to the program 6 months later after you wrote it, and you look at it, what's S? All right, so the idea is that we use names that are meaningful so that we know what they mean, so that other people will know what they mean. It's easier to understand, fix the program. Now with constants, we have a different way of doing it. We don't, when we run the words together, if we're using words like that, we use an underscore to run them together, and we use all uppercase. And again, for when assigning variables and constants, try and make them meaningful so that people reading it will know what's going on, so that you'll know what's going on. And by doing this, it's going to be more meaningful too. People will see, oh, uppercase, oh, that's a constant, it's not going to change. I'm not going to look for it to change. Oh, lowercase camel case, oh, that's a variable, probably that value will change. And so you're just having some kind of rules to make it easier for you to use the computer. Now, so the computer program. Variables and constants store data. Data is of multiple types. So when we use the word types of data, this is what we mean. Data can be numbers. Well, there's more than one type of number. You could have integer numbers, which are only whole values, or you could have floating point numbers, which would allow for decimal values. Why don't we use floating point values for everything? They take up a lot more space in the memory, right? So it just takes up more space in the memory to put a floating point than to put an integer. So if you've got something which is like a count, you don't need to have decimals for a count. Actually, it'd be a bad idea. So we use the less memory variable to do that. Characters. Now, you'd look at this and say, well, how does a character work? A character is an individual sort of letter or symbol or number. So it doesn't have to be a letter. It could be a symbol. So for example, I've been using in my program here, I've been using this symbol. The symbols that you see on your keyboard, each one of these is, it could be, each one of these that you see on your keyboard could be represented as a character, you know, so star, hash, ampersand, all of those could be a character. If you can type it in a Word document, then that's a character. Does that make sense? And so we actually have a special sort of code that we use for them. It's called Ascii, and we have 255 characters that we can use. And yeah, so what the Ascii does, Ascii code, is it takes a number, a binary number between 0 and 255, and it assigns it to a special character, and we use that. So when you're using, did I go ahead? Did I? Yeah, I think I did. So when you're using a character like 9, this is not a number. You can't do math with it. If we enter it in with quotes around it, it's not going to be treated like a number. It's treated just as a character. So you'd use that, for example, for addresses, phone numbers, identity numbers. Like we would put your student ID in 600 something or other. We would put that in as a string. So that's the next one, right? String is like a bunch of characters stuck together, right? So characters would be individual characters. A bunch of characters stuck together could include characters that look like numbers, like a student number or a cutter ID number. We don't use it as a number because we're not going to be dividing it and squaring it and multiplying it by anything, right? It's just an identification. All right. What you're supposed to look at here is the fact that, look, we've got 3 variables here. We've got a C, an A, and a B. And what this means, C equals A plus B. That's not the mathematical C equals A plus B. What it means is the variable C takes the value of whatever is the value in the variable B and whatever is in the value of the variable A, add them together and put the result into the variable C. That's what that means. And so that's what I mean is it's not like the mathematical equal to. We could have said C is equal to C plus A plus B. And that's perfectly fine in a computer language. But of course, it doesn't mean anything mathematically, because how could C be equal to C plus A? Right? C is C. It's not C plus A. That would have to mean that A and B must be 0. So I suppose that could work mathematically, but only if A and B were 0, right? But what this means is whatever is the value of C and A and B is going to be added all together and put into C. So for example, if the value of A was 2 and the value of B was 3, then C would have the value of 5 stored in it. All right, so when we talk about the state of the program, what we mean is, what are the values of all the variables and constants in the program at that time? And we use tracing for that. And so later when we do the tutorial, I'll give you all some tracing paper. And what we'll do is we'll go through one line of code at a time and we'll see what happened with the program. But I tried to do that with printed statements. With printing, we can dump out what are the values of the variables at a particular time. And so I hope you saw that in the happy birthday. In the happy birthday, we could see at this line, at this point, the count is this. At this point, the age is this. And so that's, we can do prints, or we can do some kind of paper tracing to see what is happening in the program as we go. Oh, did we not just do this? Oh, it's asking us to trace the program. Yeah, let's go back and trace it again. So yeah, we're just about done. So let's do this by looking at the program itself. Oh, we're not just about done. We got a few more to go. I better not. Really? No, I think we're done. Yeah, we're done. So yeah, let's go back and look at that happy birthday thing again. Was this happy birthday? Yeah. Happy birthday. I put a lot of, so what I'm going to do here is I'm just going to make sure that every line, we see the line number, right? So line number 3. Yeah, so this is showing us the state. This is what I mean by showing us the state. Let's do this again with a birthday, with the person is 5 years old. All right. Oh. Still got the output from a previous program. Let's do it. Okay, the person's 5 years old. What's happening? All right, so what you see, why I put the #1, that means at line 1 in the program, this is what's happening. It's asking me the age. See, line 1. So I'm going to put the age is 5, and then we can see what happens. All right, so from line 1, it went to line 2. Didn't print anything there, but at line 3, we printed the age, whatever the age was and whatever the count was. Okay, the age was 5 and the count was 0. Then the next thing it did is it went to line 4, and after line 4, it went to line, we didn't print anything at line 4, but we printed at line 5, and we can see that at line 5, it's just a happy birthday, right? Now, when we get to line 7, we're starting to see something about the state of the program. That is, we can see that the count value has changed. The age value doesn't change, but the count value does, right? And so that keeps repeating until the count value gets equal to the age value. Then we finish. Hope that makes sense. Yeah. Doing it in the Python, you don't have to write this code yet. This is going to happen to you in a couple of weeks. But I hope that you can see how the program is sort of executed there. Now, what you would do is I put a lot of print statements that were unnecessary. So to make the program work, I only put them in there so that we could see what actually happens in the program. If I put these hashes in front of it, then they're not going to be executed. And so this is what, so when the person said 5, yeah, they just get 5 happy birthdays, right? But we know that we can see above there how that actually happened. We see that that happened by the count being 0, then the count being 1, then the count being 2, the count being, and eventually it stopped. And but what the user is probably just going to see is happy birthday 5 times. That makes sense? All right. And okay, so the power of the computer, it doesn't take very long to say happy birthday 5 times. But what if the person was a bit older? What if they were like 150? How long is it going to take you to type happy birthday 150 times? That long, not very long in a computer. That's the power of the computer, right? Is that we can go through those loops much, much, much more quickly. And if we didn't have to print it, the thing that took the time there was actually printing it on the screen. The actual processing took no time at all. But what took time there was just the processing. All right, so I talked a lot. I think that I've covered everything in the notes. And so I hope that's okay with you. I'm going to stop now. Thanks, Ahmed.